반갑습니다. 밖에 계신 분 계시면 안으로 돌아주시고요. 그 다음에 시뮬레이션이 워낙 어려워가지고 아까 요나스가 얘기했죠. 한 3일 걸린다고 설명하는데, 그래서 그 디테일한 시뮬레이션에 관련된 도구를 쓰는 법하고 백그라운드 이론들이 많이 있거든요. 그런 것들은 제가 하는 교육에 이렇게 따라 한번 보시면 그때 다시 한번 정리하는 걸로 하고요. 일단 오후에 지금 준비된 게 LCC 파트가 있거든요. 제가 듣기로는 되게 잘 정리를 했습니다. 그래서 아마 도움이 되실 거라고 생각이 돼서 LCC에 관련된 거, 그 다음에 앞전에 했던 두 가지 방법으로 결과를 얻었는데 그 결과를 이용해서 LCC에 활용하는 방법들 내용이 준비가 될 것 같습니다. 오케이.
Thank you. So welcome back for this last stretch of this technical seminar, and I hope you have digested some of this really useful and at the same time quite complicated stuff with the simulation. But I think that the message, I hope that the message was quite clear, that the usefulness of being able to evaluate things over time in simulation is really cannot be overestimated. But now we're going to shift focus a bit and talk about life cycle cost. And eventually how we build up a cost model in CATLOC, but we will also talk about life cycle cost as a concept. I'm sure that all of you have heard about life cycle cost and have an idea about what it is and why we are doing it and why it's important. It's a key part of the life cycle management framework, and is really something that should be applied in all material projects in order to create understanding and visibility of cost impact of things and the decisions that we make. I searched on the web a little bit to find some definitions of what life cycle cost is. And on Wikipedia, it says life cycle cost analysis is an economic analysis tool to determine the most cost-effective option to purchase, run, sustain, or dispose of an object or process. The method is popular in helping managers determine economic consequences. From the US DAU, what does that stand for? It's like
Defense Acquisition University.
Yeah, Defense Acquisition University. Thank you. They define life cycle cost as the cost to the government of a program over its full life, including costs for research, development, testing, production, facilities, operations, maintenance, personnel, environmental compliance, and disposal. And yet another, I think, a more commercial actor had this understanding life cycle cost analysis is ideal for estimating the overall cost of projects alternatives. It's also used to choose the right design to ensure the chosen alternative will offer a lower overall ownership cost, that it's consistent with function and quality. So, from these definitions, I would say that life cycle costs rather than a figure, a number, which is equivalent to an actual cost. It is more of a tool and a process to be able to achieve cost consequences and cost impact over the entire process phases of a system's life cycle. So it's not necessarily the actual costs that will be incurred, but more a process and a tool. We will see more about that. I want to retake this picture that Oscar showed us the first on the conference about RAM, C and LCM for cost effectiveness. For this balance is really key between system effectiveness and total cost. In that case, we can achieve cost effectiveness. Because at the end of the day, system effectiveness comes to a price. And we must understand what the actions we do in order to achieve system effectiveness. I need to understand the consequences of these actions, regardless if they are in the research and development stage, in the production phase, or in the operating and support phase, or in the reinvestment and replacement phase. So, and give ourselves this possibility to evaluate cost consequences of the choices that we make is crucial in order to achieve cost effectiveness. This is also a picture that we love to show and talk about, but it is because it's quite important to have this insight. We have the life cycle phases: concept, procurement, development, commissioning, operations and support and replacement of a program. And typically over the life cycle, cost is accumulated throughout the life cycle. And we have some kind of budget or should cost limit, and hopefully at the end of the life cycle we have not exceeded that limit. And it's probably not so far from reality to say that a lot of costs are incurred during operations and support phase, because that's when you're actually executing the maintenance and support. So even though it's costly to develop a system, but if you're, for example, is an operator, you are not cashing up anything until you are acquiring the system and then operating the system. But it is the decisions that you take early on in the phase have a lot of impact on what you will pay later. So this curve shows the committed share of LCC. That means that decisions I take during the procurement and development phase will have direct impact on costs that will occur later on. And in that sense, we can also say that the possibility to influence the LCC is dramatically reduced the further in the life cycle that you find yourself. So when you're starting to operate your system, yes, there are measures that you can definitely take in order to improve cost effectiveness at that point in time, but you have much more room for significant cost impact if you are early in the phase. You can always impact maintenance during the operations and support phase by making choices that reduces the cost for maintenance. But if you can influence the system already here in terms of reliability, so it will not demand that much maintenance, that is a much better option than trying to remedy the problem further down the line. So, decisions we say that large LCC impact from decisions in early phase, but decisions at any stage that are made without LCC in mind can lead to cost, to the cost exceeding our limit. So this picture is very important to keep in mind when it comes to things like LCC. And equally important is this iceberg analogy, because what commonly is the tendency is that you look, when you are procuring a system as an operator, you are looking at the price tag of the system. What does the system cost to buy? The acquisition cost. But what you don't see at that point in time are all the hidden costs. Training, operation, maintenance, spare part, documentation, etc., etc. So therefore, it's only the tip of the iceberg that you see when you go to the shop to buy the system. And yet, this is quite common, that the system offering the most competitive price for buying the system is getting the deal, because we have not considered all these other elements. So LCC will help us to determine these other costs and be able to make this, to give us a better foundation for decision. So some areas of application that we have here: early studies and requirements analysis for specification, evaluation of alternatives, for example, as we saw in the OPUS 10 walkthrough yesterday, we compared two different systems, two different airplanes, which one is most cost effective. Tender evaluation, when you are putting out a request for an RFQ, request for quotations, the tenders come in with their offer. You must make sure that you can give them a fair comparison for their sake, but also for your own sake, because you want to make sure that you can get all the relevant information, that you are able to conduct an LCC analysis to see which one will actually be most cost effective for me in over the life cycle. And that is so common that you have, sometimes we meet customers or people in the industry or operators that are using our tools to make spare part calculations or to do other logistics analysis. And we ask them, and they say, oh, it's difficult with data, we don't have really that information. And we ask, why didn't you ask for this information when you were procuring the system? It was not in the contract. And why was it not in the contract? It is because no one asked for it when procuring the system. And maybe it's a bit simplistically said, but still there is something in that. If you are not paying attention to things like this early in the phase or in the procurement stages, and you are procuring systems, I mean, once the contract is done with the system provider, maybe they have no reason to give you more information about their system than necessary. But if you require that, if you want to be in the bidding process and compete with others, this is what we request. If you are not willing to give us this information, you have a weaker standpoint than your competitors. So it's a good way before the contract is signed to make sure that you get good information, so that allows you to evaluate the on a fair comparison with your rest of the bidders. You can also use LCC to evaluate different solutions during sustainment, system modifications versus system organizational improvements, and also for retirement planning. The example I showed you on the conference, in the conference with the part-out process to understand how you should phase out your systems and then stop repairing components, that also impacting LCC. But it's not really, it can be, but it's not necessarily for budget purposes primarily, because as you will see, LCC can be used in many cases where you will like to make comparisons and evaluations of for a certain decision, and then you use LCC as a tool of comparison, but not to really calculate the total cost, because that's something else. Some success factors to succeed with LCC is to be able to, and this I remember when I started at Systicon, we had a couple of the founders of Systicon that still worked at Systicon then, who had been involved in many projects, many LCC, as a consultant at LCC projects. So they have put together some of their best practices and experience when it comes to working with LCC. And these are, among other things, then the scope. You should not embark on a journey with LCC without having a good scope of what is your LCC analysis target. What is the purpose of it? You should have a well-defined model and strategy and an understood objective. And you also need to have all the stakeholders on board with the scope and the model, because if you don't have that and later on you come with your LCC model, you will be questioned and people will say, this is not correct, or you have made the wrong assumption, etc., and you're not analyzing the right thing. So get everyone that needs to take decisions involved and accept the model and the scope so that we can work with it going forward. You should model well-defined and relevant costs. That means that not everything needs to be included in the LCC. It's like with the model in Opus 10 of a product breakdown. It should fit the purpose. To include everything doesn't necessarily give you a better answer to the question that you want to answer. So depending on what the LCC analysis goal is, that is, you should have the right information for that. Not clutter it down with a lot of irrelevant stuff. You should build a model based upon data that is actually possible to obtain. Otherwise, your model will just be a theoretic model. So if you have good reason to understand that this information is available and you can get hold of it or you can request it, then you can have it in your model. Should have right personnel working with it, qualified people who know what they're doing. And LCC should be a KPI within the whole project, which everyone on board is to accept. Some guidelines here. you can use LCC for comparison, cost breakdown. We did that yesterday. You saw that we had two alternative aircrafts that gave us two different costs. And here it is important when you do comparison that you make fair comparison. So if you have two competing offers, two aircraft providers like in our example, and you should compare the costs, you must calibrate them against something. So if you're then using a tool like Opus 10, you can say, okay, I want to calibrate them against 90% availability. What is the LCC or the life support cost for alternative A to get to 90% availability? And what is for alternative B? Because if you compare 60% availability for B to 80% availability for A, then you're not comparing the same thing. And probably you will see that alternative B is much cheaper, yes, because they are only promising 60% availability. So make sure you get the right level of comparison, and then you can see cost breakdown. What are the elements that stand out? What are the differences between the alternatives? Not all costs are relevant to use in an LCC evaluation and comparison. For example, you have some costs that are constant for each alternative. Regardless of what alternative you choose, it's the same cost. That is not the one that's going to make any distinction between the alternatives. Cost that you have already spent, that regardless of what your choice is now, this is money that's already paid out. We should leave them out of the analysis. Also, costs that are not predictable at all should not be included, as well as cost elements that are insignificant, too small or irrelevant. So it's the same thing as with the product breakdown model. Use the things that are important, that are relevant, leave out all the details and things that you cannot impact. So focus on the costs that are distinguishing the alternatives and are relevant for your analysis. The same thing, also you can't address every single cost and try to do something about it because there's simply not time for that. So identify the cost drivers and work with them in order to see what can be done in the various alternatives for lowering the costs. And also you must have the right perspective. So you can have the user and customer cost perspective, or the manufacturer or the user customer cost perspective. So if you're an operator and you ask the manufacturer how much, and then get how they have calculated the costs, they could have left out things that you as an operator will have to consider. So for example, if you have a radar station which needs to be maintained once a month, the manufacturer might say, okay, what you need to replace these items and put it in place back there. You have that twice, multiple by 12. So the annual cost will be something, a figure. But maybe what the manufacturer does not think about is you have to pay someone to go and do that. Maybe it's far away and you have to spend the night at the hotel, and then you will perform the maintenance and you will have to get back, traveling expenses, and that will have to happen once every month the whole year. These are costs that you need to take into the consideration if you are choosing this alternative that has this monthly update. So there you have two different perspectives of the same activity. So it should always be it should always fit your purpose and not someone else's purpose. So, OPUS Suite and LCC. Of course, cost model analysis in CATLOC. That is OPUS Suite's capability in order to allow you to build up a cost model. And these are only examples. You can build up what cost model you would like, what LCC model you would like. But CATLOC harbors the cost model. And tools like OPUS 10 and SIMLOX helps you to determine things like life support costs and life operating costs directly. You can calculate the number of flights. You make a simulation to simulate the number of flight hours achieved, what is the cost per flight hour, etc. The support dimensioning as well. But it can also indirectly contribute to other phases, so like the decommissioning phase or acquisition development, where you have, for example, early phase analysis to get rough estimates of maintenance volume and operational volumes. So it's not only here where you have direct results, but since the suite can be used throughout the life cycle, it can contribute to cost elements throughout the life cycle as well. So this helps you to determine costs. So, enough with LCC theory, and let's focus a little bit more on CATLOC and how CATLOC can be used. You can open, it's an open tool, as I said yesterday. It's like when you start CATLOC, it's completely open, so you can build any cost model that you like, any cost breakdown structure. Have a quite flexible result presentation. I think you have seen a little bit of that yesterday when we used it to analyze the costs model from OPUS 10. It's excellent for cost driver identification and analysis. And it has some sensitivity analysis capabilities that we will look on later today, which are really good in order to determine the robustness of the costs. And it interfaces directly with OPUS 10 and SIMLOX results, which is a huge benefit. Some of the building blocks in the CATLOC model. The top, it's a hierarchical model, cost model breakdown. And at the top you have the cost tree, which is you can determine to have in one model, you can have several cost breakdown structures. Then you have cost aggregates on one or more level. That is a higher unit that is aggregating costs from lower units. So for example, as we saw in the OPUS 10 cost model, you have costs. Investment cost is a cost aggregate because it contains both investment in spare parts and in resources. And LSC is a cost aggregate of initial investments and recurring costs, etc. Then you have something we call cost atom, which is actually the actual cost that is calculated. So multiple cost atom can be aggregated into a cost aggregate. And the last building block is the parameter, which helps us to create arithmetic expressions to calculate cost atoms. So cost tree, cost aggregate, cost atom, and the parameter. This is an example of a cost tree. Very simple. Here you have the aggregates represent summation. So the total LCC here is aggregate termination cost. The total LCC consists of the termination cost, support cost, operation cost, and acquisition cost, which in turn consists of cost atoms. So it represents the lowest cost breakdown level. They need to have value. And the value of a cost atom can either be explicit or calculated by an expression. And here we have parameters that represent input. So for example, LCC is the sum of all the cost aggregates. LSC is the sum of the cost atoms. And system acquisition costs is the result of this product price multiplied by number of systems acquired. So this is typically how you build up a cost model, and we will see this in the tool more in detail. Now, one thing that is built into CATLOC and makes it suitable for LCC in the logistics support domain is that it's equipped with the following predefined dimensions. So one of the strong features of CATLOC is that it's possible to define a cost in different dimensions and to study the cost across these dimensions. And the dimensions are material, which represents anything that has to do with the product breakdown, the system. Task, which is everything that has to do with maintenance, scheduled, unscheduled. Station, which is self-explanatory, locational. Resources, and time. And this will be more clear when we look at the simple example how we make use of these dimensions. Within each dimension, you can define some domains. So, within the material dimension, I can define, for example, a system domain or an item domain. It might be that some costs are relevant only for systems and some costs are relevant only for items. And I want to be able to make a distinction between those costs. Same thing with tasks. You could have some costs that are related to repair and some that are related to overhaul. Station as well, depot, operational based, or so think of a dimension like an overall notion, and then you can create sub-groups within that dimension. But I think it will be better to have a look directly in the tool. But first, any questions?
혹시 질문 있으시죠? 큰일 났네. 점심 먹어서 많이 줄으시네. 일단 이분이 중요하다고 한 얘기 제가 간단하게 요약을 할게요. 혹시 LCC를 비용을 집계하는 방식으로 사용했다면 그건 아니다 이런 뜻이고요. 지금 이분이 하는 말도 몇 페이지인가 아마 써있죠? Not for budget use only 또는 비슷한 말 써있죠. 그것 때문에 하는 건 아니다 이런 뜻입니다. LCC라는 게. 우리 램비시 가이드북에 보면 AOA에서 Analysis of Alternative라는 걸 하게 되어 있습니다. 거기에 뭐로 하느냐? 코스트 가지고 해라 이런 뜻이거든요. 거기서. 그때 얘기하는 게 이제 LCC를 이용해가지고 대안 분석을 어떻게 해야 될지 뭐 이런 것들도 필요하다는 얘기고요. 그 다음에 제일 LCC를 많이 쓰는 애플리케이션 분야가 사실은 제안서 평가할 때죠, 사실은. 비용 측면에서. 그래서 아마 텐더 이밸리에이션 이렇게 써놓은 것 같고요. 그 다음에 큰 틀에서 대안 분석은 뭐 시스템을 모디피케이션한 것도 대안 분석이 아니고, 그 다음에 지원 체계를 개량하는 것도 마찬가지죠. 하나의 대안 분석이 될 수 있고. 어쨌든 대안 분석이라는 큰 틀 또는 그 범주로 전부 다 해석이 가능한 내용들입니다. 그래서 이런 쪽으로 주로 쓰이는데 우리는 맨날 이렇게 돈 계산하는 걸로 착각들을 하는 경우가 되게 많거든요. LCC라는 건 그냥 돈 짓게 해봐 뭐 이런 식의 이제 생각이 좀 있다 보니까 그거는 아닌데 자꾸 이런 식으로 얘기를 한다고 이렇게 얘기를 하더라고요. 이분들이 말씀하시는 거. 그래서 그걸 염두 좀 해주셔야 될 것 같고, 그 다음에 지금 이제 오퍼스에서 오퍼스 회의 됐건 신동이 됐건 결과를 가지고 아마 캐틀락으로 넘겨가지고 비용 모델 만드는 것들을 잠깐 보여드리는 걸로 하겠습니다. 오케이?
So, here we are in CATLOC. And CATLOC does not look exactly like OPUS and SIMLOX. It's a bit different user interface. It's still the same structure, the same, you see the tables that we have here on the left, and more or less the same looks of the toolbar and everything, but it has a different user interface. And it's because it's a bit different scenario than we do in OPUS and SIMLOX. So here we have a very simple example, the same example I think that we had on the slide priorly. Life cycle cost with a quite simple structure. So let's look at the different building blocks here. It's a system which is a quite small helicopter, only 7 items. We can see here, helicopter system. We have an organization which is a depot that's serving 3 bases. We don't have any tasks defined in this case, so I will remove this task dimension. You recognize now the dimensions that we have: the material, task, station, resources, and time. And we can put in the scenario elements from in each of these dimensions. But we don't have any tasks, and we don't have any resources in this case. But we have a 5-year period. We have a depot and 3 bases, and we have a helicopter. Within each of these dimensions, we have defined some domains. So, for example, I have a system domain, which consists of the material helicopter. Then I have the item domain, which consists of all the items. I have in the station dimension the base domain, the 3 bases, and then the depot. And I don't have any really domain in time, because each year is equally important here. If we take the cost model bottom up, we start with the parameters that we have defined. So we have a set of parameters. We have numbers of systems acquired, number of systems terminated, number of systems in operation, number of items acquired, operating time per hour, price, repair cost, repair actions, fuel cost, and termination cost. Then we have some predefined parameters like the interest rate and present value factor, etc. Now these parameters we have defined them here. So I can create a new parameter by just saying my parameter. It's given in kilometers, for example, and then I get my parameter here. So you build up your own list of parameters, or you can import from OPUS 10 or SIMLOX to get the parameters directly from that and use them. They're representing results from OPUS 10 and SIMLOX. So that's happening. If I create a new case here, you see this is a blank case. We have only the predefined parameters. But if I do build OPUS Suite cost model, I get a lot of parameters here, which corresponds to results from OPUS 10. Which then allows me to read the results from OPUS 10 directly into my cost model for OPUS 10. But in this case, we have defined ourselves these parameters. And then we have cost atoms. We have defined the system acquisition cost, cost of fuel, item investment, item repair cost, and system termination cost. Only 5 cost atoms, simple model. These could also be imported from OPUS 10. Then we have the same costs that OPUS 10 calculates. Investment in items, resource investment, etc. All the cost elements that we find here in I will use another case maybe. And we go to here we have the cost aggregates, and if we break them down even further, and add all the costs elements we have in the OPUS 10 cost model, you can see each one of these. They are the same as we have here in CATLOC. Just to show you that this is done automatically. But in our simple model, we have defined our own costs here. And then we have the breakdown structure that we call the LCC tree, which consists of these cost aggregates that are in turn calculated from the atoms. But let's go back to the parameters and look, for example, at the parameter that says operating hours. This parameter, we need to define some values for that. And typically, we would like to assign different operating hours depending on what base we are operating on. It could be that this parameter is varying with location. It could also vary depending on what system, but here we have only one system, but we could have multiple systems. So if I click on this parameter here, I can see that I have defined different value for each base, number of hours per year, or number of, no, this is the total number of hours during this 5-year period for the helicopter. And you can see that because I have defined this operating hours to be existing in the station domain and the material domain. So depending on how you would like to study your cost or your parameter, you should define them in the appropriate domain. Is operating hours time dependent? No, not according to our model here, but it could have been. So if we would have set then also set domain, then we would, if we look at the value space here, get a grid also for, we have the possibility to set this parameter for not only for base and system, but also for each year. Because now we have defined this parameter in the time dimension as well. But we don't have any values for that. It's the same regardless of year, so therefore it's not meaningful to have that. So I will unset this domain and keep the values right. And I will not go through all the parameters to see how they are set, but this is some of the fundamental concepts of CATLOC, that if you are interested in what dimensions does the cost vary and how do you set these parameters to calculate these costs. For example, number of systems acquired. We have a phase-in scenario here. So it's varying with base and with time. So we can see here, if I move time up here, that at base 1, year 1, we get 2 systems in. At base 2, we get 2 systems in the second year and 4 systems in the third year. And on base 3, we get 2 systems in the second year. So this means something to us when we are going to calculate the costs. And then we phase out some systems as well with a different schedule. That leaves us then with the result, how many systems are each year in operation. And that parameter is calculated from number of systems out and number of systems in. So as you see, I've created an expression that from these 2 parameters derives the number of systems that are currently in operation. So this is, you can use parameters, you can create new parameters based on arithmetic expressions of other parameters. And here we have a quite extensive functional editor which allows you to build arithmetic expressions with parameters. You can have logical conditions like if clauses, ceiling, floor. You can use sum, product, mean, max, and you have some time functions as well. This is way too complex to talk about right now, so don't be afraid, I won't do it now. But this is quite powerful because you can build very complex functions to calculate your parameters or your costs. So then we have the rest of the parameters here, but let's jump to the cost atoms and look, for example, at the cost of fuel consumption. So, like the parameter, the cost atom is defined in different dimensions. And the cost of fuel, we are interested to learn about the cost of fuel for the helicopter at the various bases, but also each year. So if I look at the value for cost of fuel, we can see that this is calculated individually for each year. But the cost of fuel is also calculated from the parameters that we had. Number of systems in operation, multiplied by operating hours, multiplied by fuel cost. So here again, there is an arithmetic operation that allows us to use the parameters to calculate this cost. But the cost could also be an explicit value, a cost that is not really calculated from the value. You can just override the formula with 10,000, and then suddenly you just get one value for the cost, because sometimes you don't know how you calculate it, but you know the cost figure and just want to put that in, and that's okay. But you don't have to delete the formula for that. You can just override it with an explicit value here. Oh, what happened now? And so on. You calculate, give different functions for different costs, and each function consists of the parameters that you have decided and calculated. So, with that said, I think it's time for a break in 5 minutes, but before that we should make a calculation here. So this is the resulting LCC of our simple case. 52,431,000. And depending now how we have defined the cost atoms, you can see the same dimensions down here. Material, time, task, station, resource. So if the things that we have defined, the costs that we have defined in time, they are now able to be studied in time. So if I move time dimension on the x-axis, we quickly break down the LCC to see how much of LCC is attributed to each year. So this is when I talked about that CATLOC offers a very flexible way to study the cost. Interesting. Cost is varying very much depending on year. I wonder what the cost consists of. So I click up here to break down one level, and we get the picture more clearly here. Okay, we have acquisition costs the first 3 years that we had systems acquired in. After that, we don't buy more systems, but we maintain the systems that we have. So we have operating costs, support costs, and termination costs in the end, where you phase out the systems as well. How is the cost distributed on the basis? Okay, we have base 1, base 2, base 3. I don't want to see the depot here because I'm just interested in the base, in the cost for the basis. So I will choose to look at domain base only. And I say I will also leave out the blanks. So this is, now I can just see the cost over the bases. I want them to be sorted alphabetically. So base 1, base 2, base 3. I also think that this view is very good. I would like to save it for later. So I can save my result setting. Say base cost, and it will be saved in the program. So tomorrow or next week, when I will redo my calculation, I can just go in here, base cost, I get directly back to my view here. I might want to include this in a report to my superior or something. I can go into the report settings and say I want to generate a report based on the setting base cost. I do a report. I have the tree report, but I also have this graph in a report way here. So some practical functions. But you see how this corresponds to the way that we put costs and parameters in different dimensions here. So for example, the cost of fuel consumption, year, base, and for helicopter. So in the result, we have now looked at it in the base domain. I can also look at we take the cost of fuel here, only that one. We have it in the base domain, but we can also look at it in the time domain and in the material domain, the helicopter, or all of them at once. Helicopter in time with station. So you see how the cost distributes. So this concept of dimension and domains allows me to really move around and to turn and twist and look at the cost from many different angles to get the idea of its characteristics. If we look at one last cost here before the break, the support cost here, item repair cost. Which item is most cost driving here? So I choose to look at the repair cost for material, and I can see, okay, engine is carrying most of the costs for item repairs, whereas the radio is very feeble. Or which station is carrying most repairs? Oh, the cost was not defined, of course, because in the station we have defined still the base. All repairs are done at the depot. So of course, only repair port at the depot. So I think it's time for a break. And afterwards we will look at the more complicated case and also sensitivity analysis. And think about during the break, if you have any question, we can take them afterwards.
혹시 질문 있으세요?
Material cost means the spare parts only.
Sorry?
Material cost means the spare parts only.
Or and system. It depends on how you define it. In our case here, it's only spare parts because it's repair cost. You can also, if you choose to include more, you can see also item investment cost is also part of the material. So if you look at the material dimension, you can see both spare part investment and repair cost together.
And the material cost, usually spare parts cost comes from OPUS result.
Yes. Mm-hmm.
You do not do any other optimization process in this area.
Not here.
Yes,
No.
already done in OPUS 10.
Yes.
네. 전부 다 오피스텔하고 신도에서 페라메터도 다 가져오고 여기서 그냥 집계만 하는 거예요.
그리고
CS가 들어가지고.
이렇게 리포트하고 세부적으로 보여주고.
네. 그런 역할을 주로 하고 있습니다. 근데 뭐 얼터너티브 분석을 하려면 센시티비티까지 가야 되는데 그거 이제 잠깐 쉬었다가 보여드리고 사실 오늘 내일 교육이 제일 중요한 게 사실 PBL 사례를 잠깐 소개하는 건데 그게 아마 오늘의 마지막이 될 것 같아요. 그래서 그때까지 졸리시면 좀 참으시고 차 한잔하시고 바람 쐬고 몇 시에 시작할까요? 40분에 할까요? 괜찮으시겠어요? 네, 2시 40분에 다시 시작하는 걸로 하겠습니다. Okay, we are 2:40. Yes, because
Yeah, 2:40, 45. It's
so
okay.
let's take some coffee
Yeah.
or something.
Absolutely.
Fresh. Good.
Hi.
But all I wanted to ask, in our case, we didn't transport one item or one item. We gathering many items and transport one time. So
It's
I
in blocks.
OPUS in OPUS.
Ah, okay.
How can I make gathering the spare and transport it?
Let's see here. We could have. I don't think you can do that in OPUS.
Is it impossible?
In SIMLOX it's possible, but not because you don't have that.